In this video, I'll show you how to test the equality of population proportions for 3 or more populations using the chi-squared test of homogeneity. So for this example, we have 3 different cars, so a Chevrolet Impala, a Ford Fusion, and a Honda Accord. And we've surveyed some owners of those cars to ask them if they would be likely to repurchase that particular type of car. And the results are summarized in this pivot table. So for a pivot table, the way that you get a pivot table is go to Insert and then Pivot Table. And then what that will do is it will bring up this pivot table fields over here. And if we select population and likely purchase, these are the 2 variables in the data set over here, population and likely purchase. And then if we put population for columns, we drag it into columns, and likely purchase, drag that down to rows. And then the default values is the count. And that's what we want in this case. So if we do all that, then it will create this pivot table with counts of Chevrolet Impala owners who said no, 56 of those, 69 of them said yes, out of 125 in total. Ford Fusion, 80 said no, 120 said yes, out of 200, and so on. So what I did next was I actually copied this table here, and I just pasted it as values. And the reason I wanted to do that was just to have a nice clean version of the table results without it having all these numbers in here have formulas and all kinds of things associated with them. So I just wanted a nice clean version down here to manipulate. Next, we calculate expected values for each entry in the table. So the formula for that is you multiply the row total by the column total and divide by the grand total. And you do that for each of the cells, row total times column total divided by grand total. And what you can do actually is you can just type in the formula for one cell, and then if you use dollar signs appropriately, then you can copy that formula for the other cell entries without having to retype it each time. What I mean is the dollar sign before the H there will fix this column so that when I copy it, say from here to here, the reference to H doesn't change to I, it just stays at H. And then similarly, there's a dollar sign in front of 20 here, which fixes row 20, so that when I copy down, say from here to here, it doesn't change to 21, because that would be the wrong cell that it would be referencing. And then the grand total is fixed in place, both in terms of columns and in terms of rows. So there's a dollar sign on H and on 20. So that gives us the expected totals. And then to calculate the chi-squared statistic, we need to calculate observed minus expected squared divided by expected. So that's what this formula does here. Observed minus expected squared divided by expected. So do that for all 6 cells in the table and then add them up. And that gives us the chi-squared statistic. And what I've done is I've copied that up here so that we can then calculate the p-value for that chi-squared statistic. Chi-squared distribution is non-negative, so when we're calculating a p-value for a chi-squared statistic, it's always in the upper tail. And I just need to enter 2 arguments. One is the value of the chi-squared statistic, and then the second argument, this one, is the number of populations we're looking at minus 1. And there's 3 populations in this case. minus 1 comes to 2. So 2 degrees of freedom for our chi-squared distribution. I've used a count here just to get Excel to count the number of populations. It's a little bit of overkill here. We can see there's 3, but for bigger examples, it might be nice to have Excel count that for us. So that's what that function is in there, count A. So there's our p-value, 0.0193. Significance level of alpha of 0.05 means that we reject the null hypothesis because the p-value is less than alpha. The other way we could do this is calculate a critical value. So there's the formula for the critical value. So for a tail area of 0.05, the chi-squared would be 5.991. So the decision criteria is if the chi-squared statistic is in the rejection region to the right of this, then reject the null hypothesis. So again, the conclusion is reject the null hypothesis. So the null hypothesis is that the population proportions are all the same for the 3 different types of car. And we're rejecting that, so we're concluding that there's a difference in the population proportions. But we don't know yet whether there's a difference between all 3 cars, or maybe just one of the pairs is different and the other pairs are not significantly different. So let's go through a pairwise comparison using the Marasquillo pairwise comparison procedure. So what I've done is I've summarized the data here. So these are the sample sizes, which were here, came from the pivot table actually, 125, 200, and 175. And then the proportion who said yes. So 69 out of 125 for the Chevrolet comes to 0.552. 120 out of 200 comes to 0.6 for the Ford, and 123 out of 175 comes to 0.7029 for the Honda. And what we want to ask ourselves is, if I'm comparing, say, the Chevrolet and the Ford, do those sample proportions differ by enough that I could conclude that the corresponding population proportions would differ? And similarly, comparing the Chevrolet and the Honda, do those differ by enough to conclude a difference in the population proportions, and for the Ford and the Honda as well? So we do that using this Marasquillo procedure. And first of all, we calculate the absolute difference in the sample proportions. So that's what this table does. So that's for the Chev and the Ford. This one's for the Chev and the Honda. And this one's for the Ford and the Honda. And then we have thresholds that we calculate using, it's a fairly horrible formula, but it uses the sample proportions and the chi-squared critical value and the sample sizes. So we get 3 different numbers for each of the 3 pairwise comparisons. And then the decision is if the sample difference is bigger than this threshold, then conclude that there is a significant difference. Otherwise, conclude that there is not. So you can see that for the Ford and the Chev, that sample difference is not big enough to conclude a significant difference. For the Chevrolet and the Honda, it is big enough, so we conclude a significant difference there. And for the Ford and the Honda, it's not quite big enough, so not a significant difference there. So let's see how Excel stat handles all this. So we'll do a parametric test, and this is a K proportions test. K just stands for the number of populations we're looking at, and K is 3 in this example. And then the data, it can't analyze the original data set. You have to set up a proportions table first, like this one over here. So then you have your proportions, you need your sample sizes, and then optionally you can pick the labels for the different populations. And the data can either be expressed as frequencies or proportions. It's proportions in this case, so I've selected proportions here. And I've got column labels which is referring to these. And then I'm going to do a chi-squared test and also the Marasquillo procedure. So if I OK that, we'll see if we can match the numbers we got doing the analysis by hand. So let's see. So chi-squared statistic matches 7.891. That was what we got as well. Here's the critical value. Degrees of freedom, k minus 1, k is 3. 3 minus 1 is 2. And then the p-value, 0.019. That's what we got as well. So the conclusion is to reject the null hypothesis. Given that we reject the null hypothesis, we're going to do a multiple comparisons procedure using Marasquillo. These are the sample pairwise differences, and these are the thresholds, and these all match the numbers that we calculated. And again, the same result. The only significant difference is between the Chevrolet and the Honda. And another nice way of presenting this result is we could group the cars into, put the Chevrolet and the Ford together because they're not significantly different. And then put the Ford and the Honda together because they're not significantly different. So the only significant difference is between the Honda and the Chevrolet because they're not combined in a group together.